morning. So we shall continue the discussion on Riemann integral. So we have seen some results. So let's continue. So the next result theorem. So it says if f is monotonic, if f is monotonic on closed interval a comma b and alpha is monotonically increasing continuous function is monotonically increasing continuous function on closed interval a comma b, then f belongs to R of alpha on closed interval a comma b. That is, f is Riemann-Stieltjes integral. Now, so to prove f belongs to R of alpha on closed interval a comma b, we shall prove the Riemann criterion for f. So let epsilon greater than 0. So for any n belongs to n, consider the partition P is equal to x0, x1, so on up to xn of closed interval a comma b, such that delta alpha I, that is nothing but alpha of xi minus alpha of xi minus 1 is equal to alpha of b minus alpha of a divided by n. Now, so what is the guarantee that such type of partition exists? So for that, take x is equal to alpha of b minus alpha of a divided by n for a fixed n belongs to n. This n is fixed. Now take x0 is nothing but a. Now alpha of x0, that is nothing but alpha of a, which is always less than alpha of a plus h, which is less than or equal to alpha of b. Now using intermediate value theorem, there exists an x1 belongs to open interval a comma b such that alpha of x1 is equal to alpha of a plus h, such that what is the alpha of delta alpha 1? It is nothing but alpha of x1 minus alpha of x0, which is equal to alpha of x1, that is a plus h, minus alpha of x0, which is equal to h. So similarly alpha of x1, that is nothing but alpha of a plus h, which is less than or equal to alpha of a plus 2h, which is less than or equal to alpha of b. Using intermediate value theorem again, we get there exists some x2 such that there exists x2 in our interval a comma b, such that actually it was in x1 comma b, such that alpha of x2 is equal to alpha of a plus 2h, that is which is equal to alpha of x1 plus h. Again delta alpha 2 is equal to h. Continuing like this, we get the partition P, which is nothing but x0, x1, so on up to xn, such that delta alpha I equal to h. Now it is given that f is monotonic on closed interval a comma b. We shall assume that f is monotonically increasing So similar arguments follows for monotonically decreasing. So let cap small mi, it is nothing but infimum of f of x, where x lies between xi minus 1 and xi, and capital Mi is equal to supremum of f of x, where x lies between xi minus 1 and xi for all I for all I1 less than or equal to I less than or equal to n. Now since f is monotonically increasing, what is small mi? Small mi is nothing but f of xi minus 1, because the function is monotonically increasing, and capital Mi is nothing but f of xi, and this is true for all I between 1 and n. Now consider UPF minus LPF. PF alpha minus LPF alpha. Now, which is nothing but using the definition, it is nothing but summation I is equal to 1 to n capital Mi delta alpha I minus summation small mi into delta alpha I is equal to 1 to n. Now, which is nothing but summation I is equal to 1 to n capital Mi minus small mi into delta alpha I, which is equal to now it is summation I is equal to 1 to n capital Mi minus small mi into delta alpha is nothing but alpha of b minus alpha of a divided by n, because delta alpha is nothing but h. Now if you observe, this quantity is independent of your summation, so it is alpha of b minus alpha of a divided by n into summation I is equal to 1 to n. It is small mi, capital Mi minus small mi. But what is capital Mi? It is nothing but f of xi minus f of xi minus 1, which is nothing but equal to alpha of b minus alpha of a divided by n into f of b minus f of a. Now as we take n larger, we can get this relation is less than epsilon. So for this epsilon greater than, for this arbitrary epsilon greater than 0, I got a partition P of closed interval a comma b such that UPF alpha minus LPF alpha is less than epsilon. This verifies the Riemann criterion for f, and hence f belongs to R of alpha. That is, f is Riemann still J is integrable. Okay, so let's continue. So the next result is one of the important result, and it is useful in visualizing the integrals in geometric ways. How to find the area of an integral with some finite number of discontinuity. To find the area of a function with a finite number of discontinuity. Okay, suppose f is a bounded real function on closed interval a comma b. The bounded real function on closed interval a comma b, and alpha is monotonically increasing on closed interval a comma b. Suppose that f as only finitely points of discontinuity on closed interval a comma b, and alpha is continuous at every point where at which f discontinuous, then f belongs belongs to R of alpha. So observe that f is bounded real valued function, but f has some finite number of discontinuity. So f, the point at which f discontinuous, but in that point alpha is here continuous. Then in this in that case f also Riemann Stieltjes integral. Riemann Stieltjes integrable. Okay, let's see the proof. So again, to prove f belongs to R of alpha, we shall verify the Riemann criterion for f. So let epsilon greater than 0, let epsilon greater than 0 be given. Let E be the set of points of E. Let E be the set of points of E such that f is discontinuous. F is discontinuous. Say since it's given that E is finite, say E is equal to say some y1, y2 and so on up to some ym are the points. So given that alpha is continuous at every point of E, continuous at every point of E, hence we can find a disjoint closed interval. So for this each point we can find a closed interval u1 v1 comma u2 v2 comma so on up to um vm contain we can find this a set of m's, a set of closed interval, say which are contained in closed interval a comma b, containing the points y1, y2 and so on up to ym respectively. That is, y1 is contained in u1 v1, y2 is contained in u2 v2 and so on up to yn is contained in vm, um vm. Now how such type of interval exists? So since since alpha is continuous at yj, for epsilon by m greater than 0, there exists delta greater than 0 such that now alpha is continuous at yj, so yj is between 1 and m. Now for epsilon by m greater than 0, there exists delta greater than 0 such that modulus of yj minus x less than delta implies modulus of alpha of yj minus alpha of x is less than epsilon by m. Now take uj is equal to yj minus delta by 2 and vj is equal to yj plus delta by 2. Then yj belongs to uj comma vj. Moreover, modulus of vj minus uj is less than delta using this. Now also this implies alpha of vj minus alpha of uj is less than epsilon by m. Now observe, using the continuity of alpha at yj, we are getting intervals. Using this interval, we are considering the closed interval uj comma vj. Okay. Also we get a property with this interval that this uj comma uj and vj, uj minus vj is less than delta. Modulus of uj minus vj is less than delta. Okay, now applying this is for what is it? Okay, now take take m is equal to supremum of f of x, where x belongs to closed interval a comma b, that is x lies between a and b, and take k is equal to capital K is equal to closed interval a comma b minus union of this open interval uj comma vj, where j is equal to 1 to m. Now observe this is the closed interval and this is union of open interval, hence this is an open set, and this is a closed set minus open set, hence K is closed set. Moreover, K is a subset of closed interval a comma b, so it's a closed subset of closed interval a comma b is compact, so it's a closed subset of compact set. Therefore K is compact. Now see, in the beginning f is defined on closed interval a comma b. Now I am restricting the domain to K in which I have removed the open intervals uj vj. Now uj vj contains the point yj. At yj f discontinuous, but therefore when I restrict f to K, when I restrict the function f to the domain K, then this f is continuous. Note that if a comma b, if this a comma b lies in E, means suppose the endpoints A and B are the point of discontinuity, then also by removing this, the a comma b will lies in K, but they will become an isolated point of K, hence f will continue at isolated points. Therefore f from K to R is continuous and K is compact implies f is uniformly continuous. On K. Now so for the epsilon greater than 0, given there exists delta greater than 0, such that modulus of s minus t less than delta implies modulus of f of s minus f of t is less than epsilon. Now form a partition P is equal to x0, x1, so on up to xn of closed interval a comma b, satisfying the condition. The first condition is uj comma vj belongs to P for all j 1 less than or equal to j less than or equal to n, and the second condition is no point of open interval uj vj belongs to P. And third condition is if xi is not equal to vj for all j between 1 and m, then delta xi is less than delta or equivalently if xi minus 1 is not equal to uj for all j between 1 and m, then delta xi is less than delta. Now let us take A is equal to set of all I belongs to 1, 2, 3, so on up to n, such that xi is not equal to vj 1 for all j between 1 and m. If xi is not equal to vj for any j, then we shall take that index in the set A, and we shall take the set B is nothing but set of all I belongs to 1, 2, so on up to n, such that xi equal to vj for some j 1 less than or equal to j less than or equal to m. Therefore it is not possible not possible one index in both the set. So if one index say t is in A, then xt is not equal to vj for all j. So then xt equal to vj for sub j is not possible. That is A intersection b is equal to empty, and also A union b is nothing but 1, 2, so on up to n. Now consider UPF alpha minus LPF alpha, which is nothing but summation I is equal to 1 to n capital Mi delta alpha I minus summation I is equal to 1 to n small mi delta alpha I, where what is mi? It is nothing but supremum of f of x, where x minus 1 less than or equal to x less than or equal to xi, and small mi is nothing but infimum of f of x xi minus 1 less than or equal to x less than or equal to xi minus 1 x less than or equal to xi for all I between 1 and n. Now which is equal to summation I is equal to 1 to n capital Mi minus small mi into delta alpha I. Now observe this summation is varies from I is equal to 1 to n. Using this set A and B, we are rewriting the summation as this is equal to summation capital Mi minus small mi into delta alpha I, where I varies over the set A, and plus summation capital Mi minus small mi into delta alpha I, here I varies over the set B. So let's take this as expression star. Now if I belongs to A, then xi is not equal to vj. No, if xi belongs to A, then xi is not equal to vj for all j 1 less than or equal to j less than or equal to m. Therefore delta xi is less than delta. If s comma t belongs to closed interval xi minus 1 comma xi, then modulus of s minus t is less than delta, implies using the continuity we got it is less than f of s minus uniformly continuity, we got f of s minus f of t is less than epsilon. Therefore my capital Mi minus small mi is less than or equal to epsilon. Also note that in general capital Mi minus small mi, which is equal to modulus of capital Mi minus small mi, which is less than or equal to mod capital Mi plus modulus of small mi, which is less than or equal to, now we have taken capital M as the supremum of function value in the whole of the closed interval a comma b. So capital Mi is less than or equal to m, small mi is also less than or equal to m, so it's less than or equal to 2m, and it is true for all I between 1 and n. Now using the star UPF alpha minus LPF alpha, which is equal to alpha minus LPF alpha, which is equal to, we have it is summation I belongs to A capital M minus small mi into delta alpha I plus summation I belongs to B capital Mi minus small mi into delta alpha I. Now capital Mi into small mi, whenever I belongs to A, it is less than or equal to epsilon, so it is less than or equal to epsilon into summation I is equal to into delta alpha I. Now we are taking now some summation from I is equal to 1 to n, and still it is less than or equal to it is greater than or equal to this value plus again this small capital Mi minus small mi is less than or equal to 2m, so it is again 2m into summation delta alpha j, where j is equal to 1 to m. Because observe that here I varies over b, and b has B has index from I is some index from some index between 1 and n. Okay, now so we are taking in it is as j is equal to 1 to n delta alpha j. Now this is equal to epsilon into, now I is equal to 1 to n delta x alpha I is nothing but alpha of b minus alpha of a plus 2m into it is summation j is equal to 1 to n delta alpha j is nothing but alpha of vj minus alpha of uj which is equal to epsilon into alpha of b minus alpha of a in plus 2m into now alpha of vj minus alpha of uj is nothing but epsilon by capital M. Now yeah, its j varies from 1 to m, so how many times? It is m times. So we got, which is nothing but epsilon into alpha of b minus alpha of a here mm get cancelled, so it is into 2m into epsilon, so plus it is 2m. Since epsilon greater than 0 is arbitrary for the given epsilon greater than 0, there exists a partition P of closed interval a comma b such that UPF alpha minus LPF alpha is less than epsilon. Therefore F belongs to R of alpha on closed interval a comma b. Hence observe that if F is a bounded real function on closed interval a comma b and alpha is monotonically increasing on closed interval a comma b, suppose F has only finitely many points of discontinuity on closed interval a comma b and alpha is continuous at every point at which F discontinuous, then F is Riemann integrable. Okay. Okay, so the next theorem. Okay, before seeing the next theorem, so let's take observe this. So suppose you have a function, say f of x is equal to, yeah, it is 1 if x belongs to, yeah, it is 0 to 1 where 1 is open, and 2 if it is x belongs to open interval 1 to 2. That is, f is defined on a closed interval 0, 2. Say suppose it's like this now. Yeah, say it is 0, this is 1 and this is 2. The function value, say this is 1 and this is 2. Function takes the values, so 1 when between 0 and 1, and 1 at it is not taking any value, and after 1 it takes the value 2. Now what is the area? So it says you can, yeah, now what's alpha? Alpha is nothing but now just x. So in this case, we have only one point at which function discontinuous. So therefore this f belongs to R of alpha. In particular, it belongs to R because alpha is here constant. So f belongs to constant, not identity function. So f is now belongs to, f is Riemann integrable. Okay, let's move. So Suppose f belongs to R of alpha on closed interval a comma b, and small m is less than or equal to f of x, which is less than or equal to capital M. Now, why such a small m and capital M exist? Because given that f belongs to R of alpha, so f is a bounded real valued function. Okay, now for all x belongs to closed interval a comma b, phi is continuous on closed interval small m comma capital M, closed interval small m comma capital M, and h of x is nothing but it is phi of f of x, that is a composition of phi and f on closed interval a comma b. So observe here f is Riemann-Stieltjes integrable and phi is just a continuous function on closed interval small m and capital M. Then my composition of this phi and f such that h of x is equal to phi of f of x. Then my h is Riemann-Stieltjes integral on closed interval a comma b, that is h belongs to R of alpha on closed interval a comma b. So proof. So to prove h belongs to R of alpha, we shall verify Riemann criterion for h. So let's take an epsilon greater than 0. Now given that phi is a continuous function from small m, closed interval small m comma capital M to R, moreover this is compact set, therefore my phi is uniformly continuous. So for the epsilon greater than 0, there exists delta greater than 0 with delta less than epsilon, such that modulus of s minus t less than delta implies modulus of phi of s minus phi of t is less than epsilon, using the uniform continuity of phi. Now given that f belongs to R of alpha on closed interval a comma b. So by the Riemann criteria for integrability of f, since f belongs to R of alpha, using the Riemann criterion for integrability of f, we get a partition. There exists a partition P is equal to x naught x1 so on up to xn of closed interval a comma b, such that u p f alpha minus l p f alpha is less than delta square. So I'm using here the integrability Riemann criteria. I'm using the Riemann criteria for integrability. Instead of epsilon, we are taking it as delta square. So for the delta square, there exists a partition such that UPF alpha minus LPF alpha less than delta square. Now divide the set. 1, 2, 3, so on up to n into two sets. Say A is equal to set of all I belongs to 1, 2, 3, so on up to n, such that capital Mi minus small m is less than delta, and set B is equal to set of all I belongs to 1, 2, 3, so on up to n, such that capital Mi minus small m is greater than or equal to delta. Now what is again, as you know, definition of Mi and small m. Mi is nothing but supremum of f of x, where xi minus 1 less than or equal to x less than or equal to xi, and small mi is nothing but infimum of f of x, where xi minus 1 less than or equal to x less than or equal to xi for all I. Then now observe that mi minus capital Mi minus small mi is less than delta and greater than or equal to delta. It cannot be simultaneously. Therefore, A intersection B is equal to empty, and A union B is equal to 1, 2, 3, so on up to n. Now let's take capital Mi star is nothing but supremum of h of x, where x minus 1 less than or equal to x less than or equal to xi, and small mi star is equal to infimum of h of x, where xi minus 1 less than x less than or equal to xi, and for all I. So observe, capital Mi and small mi is for h, and is capital Mi star and small mi star for h. Now let's take k is equal to supremum of modulus of phi of t, where this t is between small m and capital M. So what's the guarantee that such a supremum exists? Since given that phi is a continuous on compact set, so continuous function on a compact set is bounded. Now for any I belongs to A. So if I belongs to A, yeah. So yeah. For I belongs to A, if s comma t belongs to xi minus 1 closed interval xi minus 1 comma xi, then f of s comma f of t belongs to the closed interval small mi comma capital Mi. Therefore modulus of f of s minus f of t is less than or equal to capital Mi minus small mi, which is less than delta, since I belongs to A, which implies modulus of phi of f of s minus phi of f of t using the uniform continuity of phi is less than epsilon. That is h uniform continuity. Therefore which implies now phi of f of s is nothing but h of s minus h of t modulus is less than epsilon. Now delta into summation delta alpha I, where I belongs to B, which is equal to summation I belongs to B into delta alpha I, which is less than or equal to summation I belongs to B. Now see, whenever I belongs to B, we have m of capital Mi minus small mi is greater than or equal to delta. Therefore this del less than or equal to capital Mi minus small mi, now into delta alpha I. Now which is less than or equal to summation I is equal to 1 to n, because B is a subset of 1, 2, 3, so on up to n. So which is in summation I is equal to 1 to n capital Mi minus small mi into delta alpha I, which is equal to UPF alpha minus LPF alpha. But using my Riemann criteria, by applying Riemann criteria for integrability of f, we got this is less than delta square. That is, we got delta into summation. So delta into summation delta alpha I, where I belongs to B, which is less than delta square implies summation I belongs to B delta alpha I is less than delta. Now for any S belongs to closed interval xi comma xi minus 1 comma xi, we have f of s belongs to small mi comma capital Mi, closed interval small mi comma capital Mi, which is contained in closed intervals small m comma capital M. Now which implies phi of f of s is less than or equal to k, because k is the supremum of phi, and that is phi of f of s, nothing but it is h of s. So modulus of h of s is less than or equal to k for all s belongs to closed interval xi minus 1 comma xi. That is we have, so minus k is less than or equal to h of s, which is less than or equal to capital K for all s belongs to closed interval xi minus 1 comma xi. So therefore minus k is less than or equal to mi star, and capital Mi star is less than or equal to k. See this. Yeah, we have small mi star is nothing but infimum of h of x in xi minus 1 and xi in the closed interval xi minus 1 and xi, but here h of h of s is greater than equal to minus k in this xi minus 1 and xi. So minus k is an lower bound and small mi star is an least greatest lower bound. Therefore minus k is greater less than or equal to mi star. Similarly capital Mi star is the supremum of h in the closed interval xi minus 1 comma xi, but k is an upper bound of h in the closed interval xi minus 1 comma xi. Therefore Mi star is the, since Mi star is the least lower bound, Mi star is less than or equal to k, and this is true for all I between 1 and n. Therefore consider Mi star minus small mi star, which is nothing but modulus of capital Mi star minus small mi star, which is less than or equal to mod capital Mi star plus mod small mi star is less than or equal to 2k, because Mi stars, Mi small mi and capital Mi stars, small m capital Mi star and small mi star, and supremum and infimum of h, but what is k? K is the supremum of h. K is the supremum of h. Now consider u p h alpha minus l p h alpha, because we are in a route to find the to verify the Riemann criterion for h, Now this is equal to summation I is equal to 1 to n capital Mi star minus small mi star into delta alpha I. We have observed how we are getting this from the previous two to 3 results. Okay, so which is equal to, again it is summation, so we are changing the since here its summation varies from I is equal to 1 to n, but also I know that A union B is nothing but 1 to 3 so on up to n, so I am taking summation over A, that is I belongs to A. Yeah, so let's so it is I belongs to A, into capital Mi star minus small mi star into delta alpha I plus summation I belongs to B into capital Mi star minus small mi star into delta alpha I. Now which is less than or equal to, now whenever we have seen that Mi star minus Mi star, whenever I belongs to A, is less than epsilon, so it is less than epsilon into summation I belongs to A delta alpha I plus again this is summation I belongs to B into, now Mi star minus Mi star is less than or equal to 2k into delta alpha I, which is equal to epsilon into summation I belongs to A delta alpha I plus 2k into summation I belongs to B into delta alpha I. Now which is less than epsilon into delta, because summation I belongs to A delta alpha I is less than delta, and plus it is 2k into whenever I belongs to B, delta alpha I is also less than delta. I think we have made some mistake here. Yes. Made a mistake. Wherever I belongs to B, summation I belongs to B, delta alpha is less than delta. So this one is less than epsilon into summation I belongs to, yeah. So let's take I belongs to instead of, yeah, okay. Let's write once again. So it is k 2k into delta, because this quantity is less than delta. Now since it is I belongs to A, we are taking is I is equal to 1 to n delta alpha I, because I belongs to A is a subset of set 1, 2, 3, so on up to n. So which is equivalent, which is yeah. So now take this is epsilon itself. Now what is this? It is nothing but alpha of b minus alpha of a plus 2k into delta. Instead of delta is less than epsilon, so it is less than epsilon into alpha of b minus alpha of a plus 2k epsilon, and that is alpha epsilon into alpha of b minus alpha of a plus 2k. Since epsilon greater than 0 is arbitrary, we get for the epsilon greater than 0, UPH alpha minus LPH alpha is less than epsilon. Therefore, H belongs to R of alpha on closed interval a comma b. Thus we got if f is a Riemann series integral and phi is a continuous function, then composition of phi and f, that is phi of f of x, is also Riemann series integral. Thank you.